one normally has a notion of time which is universal. So we would think that a moment of time here would be identifiable with an equivalent moment of time on the Andromeda galaxy, for example. Whereas according to relativity theory, there isn't a universal notion of time. Time is more a local thing. So one imagines, according to relativity theory, you think of space and time together as one four-dimensional continuum. So normally we think of space as separate from time, but according to relativity, first of all, special relativity, then you have a notion of time which depends on your motion. So when we go to general relativity, it gets more complicated because it's not just one's own motion. You have to think of time if you want to be very precise. And now measurements of time are extraordinarily precise. So one can have a clock which is extremely accurate. Now, when I say accurate, this means that that clock, you have to think of that clock in space-time. In space-time, you think of space and time together to give you a four-dimensional picture. Now, on any world line, now a world line is the history of a particle. So if we think of that clock as describable as a single particle, say, then its world line will be the history of that particle. And along that history, there will be a very well-defined notion of time, which is extraordinarily accurately measured. But if you have two, say you have a clock here and another clock together with the first one, and then they separate, travel with very great speed, and then come together. When they come together, the length of time experienced by each will not be quite the same. And these slight differences are now measured very precisely. One of the effects of relativity is also that gravitation, this is now general relativity, that gravitation affects how clocks behave. And in particular, if you have a clock at the bottom of a well and the clock at the top of a tower, and you set them very precisely, and then you take them apart and set them there, and then you bring them back together, you will see that the time passed by the one at the bottom of the well will not be as great as that passed by the one at the top. Now, these are very closely measured now too. And in fact, I can have a clock stationary here and another clock here. And the difference in the time rates can be explicitly measured. So it's very remarkable how very precise this notion of time is, but it depends upon the history of the clock. So even if they may start at the same event and come back again, the total time elapsed will not be quite the same. But these differences are extraordinarily small. So in ordinary experience, one doesn't notice these differences at all. But one has clocks using quantum effects, which are so precise now, that not only can we measure these differences, but we can use the differences in the time rates to, well, measure gravitational fields, and you can actually use them for, say, prospecting for minerals and tell you how much mass there is there, because it does affect the rates of clocks. So these things play their roles in actual.
Actually, it has always challenged me conceptually to think about this, because at some point you will really be able to appreciate a difference in time between a spatial difference that is extremely tiny, no?
Yes.
But the clock itself has a spatial, as a size. So you will start like having different times within the same clock.
Well, you have that, but these are very small.
Yeah.
Let me make a point, which is really a crucial one with regard to these discussions. They're the two most famous equations of 20th century physics. One of them is Einstein's E equals mc squared, which told you that energy and mass are equivalent. The c squared is just a scaling between the two measures. So mass and, Yes, mass and energy are equivalent. Now, even before Einstein, there was Max Planck, who had produced his famous equation, which is E equals h nu. Now, h is a different constant, not the speed of light. This is what we call Planck's constant. And nu is a frequency. Sometimes people call it f. But anyway, the formula is E equals hf or E equals h nu. And that tells us that energy and frequency are equivalent. So you have something which oscillates, or something that has a definite energy that oscillates with a definite frequency. Now, if you put these two together, first Einstein tells you that energy and mass are equivalent, and Max Planck tells you that energy and frequency are equivalent. This tells you that mass and frequency are equivalent. So if you have a stable, massive particle, it is a clock. It's a clock with extraordinary precision. Now, you can't normally quite directly measure this. It's a very high frequency. You have to sort of tone it down by various devices to get you something which you can actually register. But ultimately, the precision in the clocks comes down to this very simple fact that in modern physics, frequency and mass are equivalent. So a stable massive particle is a clock. And it's a clock of very precise character. But it does move, and if you have two of these similar particles and they move apart and come together, then you may find that the time elapsed is not quite the same. And because of this precision that you have in this notion of local time, call it, we can actually measure these differences. And the theories also can be tested to very great precision. And in fact, general relativity is extraordinarily precisely tested. So these things are pretty reliable. There is something in my own work, however, which is looking at the opposite side of this in a way. That is, if you don't have mass, then you don't have a notion of time. Now, there are certain features of physics where you don't have mass. The most familiar one is with Maxwell's equations. See, Maxwell, with his beautiful equations, tied together electricity and magnetism into a theory which involves both. And part of this theory are the waves that you get, the Maxwellian waves, which constitute light. So light is a very small frequency, certainly 1 octave basically of frequencies, which are the lights that we see visually. But we have, on the one hand, very, very high frequencies where you have gamma rays, X-rays, and on the other hand, you have low frequencies like radio waves, and they can be extremely low. They may see extraordinary low frequencies can be measured. So you have a huge range of different frequencies, only a very small range of this, 1 octave, so to speak, which is directly visible to us as light. But nevertheless, these equations govern the way electricity and magnetism, how they fit together in a beautifully accurate way. Now, as part of this, I should say that these equations have a curious feature, and that is if you don't have any mass, then they are completely independent of the scale of size. So I have this cosmological scheme, which I believe has, in recent observations, some important confirmation, which is controversial, I should say.
The conformal cosmology.
Cyclic cosmology model. Now, you see, according to this, there are two places where mass begins to lose its role. One is the very remote future, mainly because the very remote future will be dominated by photons, and photons have no mass. But there's a little more to it. You have to have...
Is this because the mass is dilute, or why do we expect that in the infinite...
Well, there are two reasons. One is just because it gets diluted, that's right. Black holes swallow a lot of material and they radiate very, very little for a long time, though. And photons are running around. You do have things like hydrogen, which run around in empty space. The matter of galaxies, on the whole, will be swallowed by black holes. We have a big black hole in our center, which will probably swallow about half the mass in the galaxy eventually, but over a very long period. It's in a cluster. You have other clusters, and they will probably mainly, the black holes will come together and they will swallow this material. So you have a lot of photons running around and a few black holes. You also will have things like hydrogen. Now, according to the CCC proposal, the Conformal Cyclic Cosmology proposal, the mass actually eventually decays away. This is a feature of having what's called a cosmological constant in Einstein's equations. In 1915 is usually considered the birth of Einstein's general relativity. But in 1917, he introduced another term, which is called the cosmological constant. He wanted a static universe which didn't expand. This was soon shown to be wrong. It was already, if Einstein had known more about the observations, he might have been worried about this, because Hubble had, well, even before Hubble, there were observations showing that the universe was expanding. And then Hubble convincingly showed this was the case. And so this showed that this model that Einstein wanted of a static universe was not really representative of the actual universe. And so Einstein regarded as his greatest blunder the introduction of this term. What his greatest blunder was, perhaps, on the other hand, that he considered it as his greatest blunder, because this blunder turns out actually to be true. That relatively recent observations, that is early in the 21st century, people made observations of distant supernovae stars, exploding stars, and they concluded basically that there was this exponential expansion, which would be an effect of Einstein's cosmological constant. So it really tells us that Einstein's blunder was actually not a blunder, it was correct, which is rather an ironic thing that he should have regarded that as his greatest blunder. Yes, the evidence is that this cosmological constant is present, which means that the universe will go into this late phase of exponential expansion and expansion and expansion, and the mass will fade out, and there will be nothing left of any consequence except black holes. These black holes will evaporate away by Hawking evaporation, and over a huge, huge period of time, we have to think of something like, well, a googol years, that means how many years? 1 followed by 100 zeros. That's a googol. I'm not sure whether when I talk to the screen, the zeros go this way or that way. I think it reverses.
Yeah, it reverses.
I'm confused. Anyway, from my point of view, they go that way.
Actually, is there an estimate of how many black holes we will end up with?
Well, there's an estimate, but then they will evaporate, you see. So they will they will all disappear. In the estimate for this, the length of time is about 10 to the power 109, 106, 10 to the power 106. So when I say 10 to the power 106, I mean 1 followed by 106 zeros. That number of years, pretty well all the black holes will have evaporated away, and there will be nothing left but radiation. Now this is radiation, basically Maxwell's equations. And so according to my scheme, there is no way of measuring the scale. See, when I say how accurately you do have a measure of time, this depends on the presence of mass. When you have no mass, then you lose the scale of the universe. So big and small become effectively equivalent. Now, the other end of the scale is the Big Bang. And there it's a completely different reason. There you have energies are so huge when you get back and back and back into the Big Bang, that the mass becomes such a small fraction of the energy, it becomes completely irrelevant. So when you get back to the Big Bang again, you have a situation, you have no mass, and therefore the universe loses track of its scale. Now it's a completely wild idea, but it solves so many problems in cosmology. One of them being this famous principle of physics known as the second law of thermodynamics, which tells you that notion known of entropy, this is sort of a measure of randomness. This measure of entropy is increasing all the time. So according to the second law, entropy or disorder is increasing. Now, when you get to black holes, the entropy gets absolutely enormous. According to the Bekenstein-Hawking formula, which I very much agree with, that formula tells you that the entropy is absolutely huge in black holes, and that's where it goes. And when they evaporate away, well, there's some question about what happens to it. But in my model, the radiation from these black holes, because of the exponential radiation, expansion of the universe, even though you think of this radiation as getting away from the black hole, it doesn't make any headway at all. It's more or less concentrated at one point. So in the crossover from one eon to the next, this radiation is concentrated in one point, and it bursts through into the next eon at what I call a Hawking point. Now, you don't see the Hawking point directly because radiation does not escape. It does not escape for roughly 380,000 years. This is accepted standard cosmology. 380,000 years it takes before radiation can finally break loose and be observed.
Is the coupling between electrons and photons you are referring to? Okay.
It has to do with the coupling, and you find that it manages to escape when the temperature gets to this point, and you get decoupling. And well, there are various features which are more or less the same, the decoupling and this last scattering, which occur at this 380,000 years. And then that light is what we see. This is the cosmic microwave background. Now, you see that spreads out from that point, from one point to what you can tell pretty exactly, what would be about 4 degrees in the sky. So we're looking at a degrees, that's an angular degrees.
Very tiny.
Very tiny. The moon, the full moon, is about half a degree. So 4 degrees is about 8 times the diameter of the moon. So the Hawking point spreads to about 8 times the moon's diameter. So you see a raising of temperature inside that region, which is very specific. And in our observations, we look at the Planck data. There's 2 satellites. One was the original WMAP satellite, which looked at the microwave. Well, there was an earlier one too, but it didn't have the facilities to look for the temperature variations in the sky. So the WMAP one did. And the more modern one, which was more sophisticated, the Planck satellite, again looked at these temperature variations. Now, if you look very carefully for these Hawking point, the spreading out of the initially a point spreads out to 4 degrees in the sky, or 8 times the moon's diameter, just at that size, and you see them at that size. And the confidence level is what well, that's the probability that this is not an effect by chance, we can claim is 99.9%, 99.98% confidence. So that's a pretty strong level of confidence. There are other effects of the conformal cyclic cosmology people get confused by, because when black holes collide, they produce gravitational wave signals, and they would produce rings. And we claim those are seen too. But they are confused by people with the other signals because they're completely different. But they're probably seen too, not with such a confidence level. We see them with about 99.4% confidence.
I think I have been looking at one of your paper where you analyze the CMB map to identify these circles. But then I was also asking myself, should we really see many of them, since there will be many black holes at the end?
Yes, you probably see a lot more of the collisions, but then the signals are much weaker. So we do see lots of them. We see in the thousands. You have to make sure they're in certain places. So the radiation, our past cone has to catch it. So you don't see them all. The ones that you see a much smaller fraction of would be the Hawking points, because those you have to see directly. Our pass cone has to hit the place where they decay. So you see only a very small fraction. We see about 6 of them with real confidence. When I say 6 with confidence, we may see quite a few more, but they may not be real. Why I say these 6 are pretty confident? Because we see them in both Planck and WMAP at exactly the same places. We see other indications which are different, but these are the 5 strongest ones in the Planck data are in exactly the same places in the WMAP data. And there's a 6th one, which we also see not quite so strong in the Planck data. So we see these 6 points, which we feel pretty confident are there. Now there's another effect too we might see, because if they had earlier collisions with other black holes, which they probably had, then we might see them too. And they have signals which are of the first kind, the rings, but they have to be seen edge on. So you have to be careful how to see them. And we claim that half of the 6 we see do have we can see that too. Three of them we see a pretty clear indication of a point very close to the Hawking point, to certainly within the I forget how small, half a degree or something, something like that. I would have to check on them. And so 3 of them we do see evidence for that. The other 3 we don't. It's quite possible we'd miss them because the collisions have to be strong enough, and we only look for ones where you see 3 from the same point. So if there were only 2, we wouldn't see them.
Maybe another question that I had regarding this idea is that you imagine this chain of universe, not these eons, and each one of these in practice lasts infinite time, no?
Yes, you see, that's the thing.
It's just from the reference frame, of the photon. Of course, this infinite time is nothing because the photon has no mass, and so infinite time doesn't really have a meaning. But from our perspective, the next thing will never happen.
I think this is the thing, you see, one reason why people find this model so hard to get their minds around, and I think I can understand that. We have a notion of time which is very clear and very precisely mirrored. I should say, of course, psychological time is very much influenced by all sorts of things, drugs and sleep and goodness knows what. So our feelings of time, when in a coma or goodness knows what, all sorts of things affect our feelings of time. So that is changed in many ways. Nevertheless, we can abstract from that in physical time that we can measure with clocks, something very, very precise. And this is so precise, as I was saying earlier, that we get used to the idea that this time is a universal notion. But as I mentioned, the way I've described it is defined by things with mass. And when they don't have mass, that notion of time begins to lose its meaning. You can have a thing kind of conformal time, which is not so precisely defined, but which gives a measure of the entirety of the eon, starting at the Big Bang and ending at the infinity that we normally think of with the normal measures of time. But it's a time, if you like. It's time infinity. But it's a realizable time because it is, according to the photons, certainly a place where they cross over into the next eon. And if these photons have long enough wavelength, they would have to be certainly radio wave photons of long wavelength. Otherwise, they wouldn't get through. They would get scattered and so on, right, very close in the next eon. But if they're very long wavelength, they can get through and provide signals which could be seen in the next eon. So there is communication of some sort possible. Whether you could actually use that in any way, one civilization to communicate with another one, I have no idea. But in principle, that's not impossible in this scheme. A nice thing to speculate about. We could write science fiction stories about that.
So it doesn't really make a lot of sense, let's say, to write down a timeline and to put these universes like one after the other, also because then we would be speaking of a time outside the universe, wouldn't we?
I would agree with that, but this is not a time outside the universe. It's just a time measure which is useful for cosmological purposes. It's not the time that you measure on your watch.
It's a parameter.
But it's at present, it would be very accurately the same. It would only deviate from it from very, very long periods of time or very close to the Big Bang, where one would go as the square of the other. That's when you get close to the Big Bang, they're not quite the same. When you get into the remote future, they're not the same at all. But nevertheless, it's a very good measure of time when you talk about cosmology. It's not an external time. It's not as though we're looking outside at this picture of these nested, expanding universes. That's a nice picture which we can put into our minds to think of how to picture it. But nevertheless, there is a pretty well-defined notion of conformal time. It's measured as a sort of average time, spatially average time. It's not a notion which would be very precise at a particular location. But as an overall measure of time, it's pretty good. And that measure of time, you could say it's one unit of cosmic time from the Big Bang to its, normally we'd say infinity, when its crossover moment takes place. So each one of those is one unit of cosmic conformal time. You see, the problem one has is the singularity asymmetry, which, I mean, in the early 1960s, I was involved with the singularity theorems, and Stephen Hawking and Bob Gerroch and others produced a lot of nice theorems, Brandon Carter, and these theorems don't distinguish between the past and the future. So you have theorems which tell you that with certain conditions, you will have singularities in the future. That's in gravitational collapse. And in an expanding universe, you have singularities in the past. And so, like most people, I thought, well, these are the same phenomenon, and we were going to need quantum gravity or something like that to resolve both problems. And it took me a long time. I had a long period of thinking after, I think it was a conversation I had with James Peebles. I think I was in Princeton for a few months, and one of the things people in Princeton tended to do was to go to conferences at Stevens Institute. They were called the Stevens meetings in Hoboken, New Jersey, just across from New York. And the people from Syracuse and the people from Princeton would tend to meet and have very interesting meetings. I used to go to these. And there was a meeting, and Jim Peebles was sitting in a car, and he was going off to the meeting. I was going in another car to this meeting too. And I took my opportunity to ask him a question that had been puzzling me. I said, why is it that in general relativity, we have all sorts of different kinds of models with singularities, very complicated and very different from each other. And you cosmologists never consider any of them. You just look at these very simple Robertson, Walker, Friedman singularities. And why do you do that? And he looked at me and he says, because that's what the universe is like. And I thought, that was a great evolution. I mean, I think he was thinking of the cosmic microwave background, and it's very uniform. And so this led me to thinking, what was so special, very different about the Big Bang? Up to that point, I just thought, well, it's just another singularity. It's not just another singularity. It's something very, 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 very peculiar. And the more I learned about entropy and black holes and all that, the more peculiar and more peculiar it became in my mind. There was something very different about it. So I went through my life thinking for a long time that this must be, sure, it's quantum gravity. Everything must be quantum gravity when curvatures get to 10 to the minus 33 centimeters in radius. Yeah, of course. But then I began to think, well, it's very different. And I proposed this hypothesis, well, the bio curvature hypothesis, says they're different. And I was trying to think of how you could have a quantum gravity theory which was grossly time asymmetrical. And it wasn't until I thought of CCC that I was able to ditch that idea and realize that the difference is that the singularities are not in the Weyl curvature. Well, I knew that. Not in the Weyl curvature, in the Ricci curvature. And if they're in the Ricci curvature, you can scale them away. Well, this was work partly done by Paul Todd, who was a graduate student of mine, and he explored this and he postulated that you could stretch the Big Bang and make it smooth, and that meant the Weyl curvature had to be finite. And then I proposed CCC, which made it have to be zero. So it is the Weyl curvature hypothesis, and it only works if the Weyl curvature is zero. And if the entropy is solved basically because it gets locked into black holes, and the black holes more or less, well, they radiate some, but then the expansion kind of dilutes that. And in fact, all that radiation goes into the Hawking points anyway. So it all goes into the Hawking points. And so that's where it goes. And the Hawking points, well, we have to understand them better. And that's the entropy, if you like, gets destroyed in the Hawking points. It comes out again, but in a very diluted form. And you certainly don't get nearly so much entropy in the Hawking points that you would have had in the black holes.
Maybe it's really worth mentioning this problem that you were saying about the initial and final condition of the universe and what kind of paradox enters and this idea that the entropy has always to increase.
Yes, well, I mean, this is what been driving me for so many years, puzzling me. And you see, I think people were confused by inflation. Somehow, well, some are confused and some are led down very curious routes. This presumed very early expansion within the first 10 to the minus 32 seconds, whatever it was, of the universe's expansion, this inflationary expansion, which was supposed to have taken place in a very early universe, to explain all sorts of things, some of which needed explaining, absolutely true, but inflation never explained the big ones to me, namely why you got a Weyl curvature hypothesis. Why was the Weyl curvature zero? Why was the universe so smooth? And people say, oh, the inflaton fields, it doesn't. It only does if it's already smooth. If you look at the models, you have to start with a Friedman-Robertson-Walker model pretty well, and you perturb away from it or something. None of these models start from a generic singularity. You don't get anywhere. Inflation doesn't get a start, doesn't do anything. So, and you can see that by reversing time. And
so you need, let's say, a very special initial condition for the universe.
Even with inflation. Yes, that's right. Well, people tend to argue for that. Yes, so they say, oh, very complicated in this little tiny place. But then I don't think it's a good argument, because you just work out the chances of finding this very, very smooth little place. Finding a bit bigger one is much more likely. How much more likely is that than that? Huge. We see our universe, then people use an anthropic argument. Say, well, we have to be in a universe with the expansion because we wouldn't be anywhere, you see, or something. So use an anthropic argument. The universe is here because we're here and we're here to observe it. But it only tells us, okay, how about our galactic cluster? Let's just go for that. But then you didn't need it for later on. Why do you keep looking further and further? You see that it just looks the same. It doesn't explain why it's the same all the way out there. It's no explanation. So I've never accepted any of those anthropic type arguments. They just seem to be quite wrong. Not just...
Well, at least they don't bring you anywhere. I mean, what is the explanatory power of this argument?
They don't get you anywhere. No, I agree. I don't think they get you anywhere at all. I mean, they're interesting arguments. I don't poo-poo them as such. I think you might have to take seriously some aspects of these. Why do certain constants come out just so that, well, there was originally the Hoyle coincidence, which was the fact that there was a particular, what was it, energy level of carbon which allowed the 3 carbons to come together so you could build up elements heavier than carbon, oxygen and heavier elements. And that was an important thing, which needed particle physics to be just right to produce this energy level. And so this was the origin of certain types of anthropic arguments. Now, I never took them too seriously myself, because it's never quite clear if you had a completely and utterly different kind of universe, how do you know what kind of numbers would have been relevant? It's very hard to speculate on such things. Anything which is quite like our universe, yes, maybe it needs this, but that's a bit of a circular argument. So I don't know how to use these arguments. I don't dismiss them entirely, because I think there is some relevance to them which we haven't found the argument for as yet. It would be very interesting to know how these numbers, because you have, the Dirac coincidence numbers, you've got many numbers where some of them are explained. It's very beautiful, wasn't it? Dirac worked out the ratios of different fundamental constants, and very important piece of work, really. But one of these was to work out the age of the universe in proton times, I think it was. He didn't use Planck units. He used the frequency, proton frequency, and he came to a number like 10 to the 40. And he sees 10 to the 40 also in the ratio of the gravitational to the electromagnetic. I can't remember which it is. It's either the nuclear or electromagnetic force. And you had 10 to the 40 there. And it looked like a pure coincidence. So he thought one of them is the date, because that's the age of the universe. And so therefore the other one must change, because the date changes. The date is just a number which evolves with time. And therefore these other numbers also must change. That was shown to be wrong. So it became a sort of mystery, which I suppose became a big anthropic argument. But the resolution was found, well, independently by Brandon Carter and Bob Dickey. Bob Dickey a lot earlier. I don't think Carter knew about it. I heard it from Brandon Carter, which was simply to look at the processes which go on in main sequence stars. And you work out the sort of lifetime for a main sequence star. And you would say, if life comes about throughout somewhere in the middle of the history of a main sequence star, and then this life looks out at the universe and see what the age of the universe is, it automatically comes up with this coincidence. But it comes out with it because it's in the way that the evolution of the star has developed. And I thought that was an amazing piece of work. So it shows you that this thing, which looks like an amazing coincidence, you can explain it just from standard physics. It may be that some of these others can be explained in that way, which would be very interesting. What kind of explanation we find, I don't know. And it's a big challenge, but it's a challenge which you have to be careful about. And also look to science fiction occasionally to sort of straighten your mind out. There's a lovely story by, what's his name? I have to remember the story now. It's about life on a neutron star. And the life is developed in such a way that the timescale is not ordinary chemical processes, but nuclear processes. So it works so much faster. And so the beings on this neutron star evolve at an enormously faster rate. And by the time the astronauts come, this neutron star comes close to the sun. And the astronauts go and they look at the neutron star. Robert Forward, he was the author, I think that's right. And so the astronauts look at the neutron star and they get signals, and they, in the time that they're communicating with the people on the neutron star, their evolution develops so fast that they get ahead of the humans, but they're stimulated by seeing this star coming along, which they mistake for some signal from. And they have a religious period where they go through, and this star is just the satellite approach, and you see. So
it's an interesting intellectual exercise, no?
Yes, I think it's a very nice story. Yes, let's think about all sorts of things in the story.
So we mentioned a couple of times that we expect the law of physics to be symmetric in time. No, if I do an experiment today or tomorrow, I expect to have the same result. So the law of physics should be invariant under time translation. But nevertheless, we know that we see a clear arrow of time, or that's at least what appears to us. And so, how do you understand this? So, do you believe that the law of physics should be time asymmetrical at some fundamental level as well, or not really?
I think I've had different views in my life about this. You see, before I had CCC, I think I strongly believed there must be a C violation, not just CP and all these others. Well, yeah, it's complicated because you have CP violation, you have CPT violation. Do you have CPT violation? Well, there's a good question, you see. But you see, do we have violations of some of these notions in some basic way, which might violate CPT? I wasn't too ashamed to maybe claim that there might be violations right the way through. But with CCC, it's different. It really propagates itself in a way which preserves the entropy. You see, the uniformity of a very remote universe, apart from the Hawking points. It's very uniform apart from Hawking points, and they're just tiny little bits in the whole measure of the crossover surface. You see, I changed my view before thinking too much about Hawking points a bit, because when you do the conformal transfer, you've got to invert your conformal factor, but that doesn't affect the Planck's constant, you see. So that inversion does not affect the phase space volumes. The only thing you would might affect how you measure them, but I don't think on a big enough scale. I think it has got to be in the Hawking points, because that's where all the Hawking. See, some people say, well, half of it goes into the radiation, well, it doesn't matter too much. It doesn't matter whether half of it goes into the Hawking radiation and half of it goes into the singularity, the pop, if you like, at the end, because that is a genuine singularity where the information gets lost. Doesn't matter. It all goes into the Hawking points. So where on the CCC, that's where all the entropy has gone. And I think I'm not going to contradict myself on that one too soon, I hope. And so well, who knows what physics goes on in there. But what is allowed to go through into the other side is basically very, very hot physics. I don't know what very, very hot physics is, but it's constrained by the mass defined appropriately. There is an invariant notion of what you could call the mass there, I think, whether it's a mass. Again, I'm talking a little bit ahead of myself here, but you could work out what the mass of that supermassive black hole was from the strength of the Hawking point. And that would tell you a measure. And from that, you would know what the Hawking. I think most of the entropy in the Hawking points. It's almost entirely in the Hawking black holes now, even now.
Yeah.
Vastly more in black holes than anything else. So it's only going to go up, and that will be more and more in the black holes. So it's almost entirely in the black holes. And that goes into the Hawking points. So that's where it all goes.